was that when was an example involving a Cobb-Douglas production function, then we knew its associated cost function, and from that associated cost function, we recovered the Cobb-Douglas function. Beforehand, we only knew that using that formula, we would obtain not necessarily the original production function, but another production function which is equivalent to the original in the sense that it has the same associated cost function. But we found exactly that one. Was it by accident? Was it just a coincidence? The answer is no. There was a reason. The reason is that the Cobb-Douglas function, which was the original production function, is very regular. It has the nice properties a production function has to satisfy. It's quasi-concave, non-decreasing, and upper semi-continuous. So now we are going to prove that what happened yesterday for that Cobb-Douglas function will always happen when the production function is quasi-concave, non-decreasing, and upper semi-continuous. So the theorem says as follows. Let f our production function be quasi-concave non-decreasing and upper semi-continuous. And let's see be the cost function associated with it. Then f of x is equal to the maximum of y inner plus such that c of yp is less than or equal to px for every p in r plus plus n, and this is true for every x. Okay, so it is saying we have a nice production function, quasi-concave, non-decreasing, and upper semi-continuous. Then we apply the right-hand side to C, to the cost function associated with f, to obtain an equivalent production function, a production function that will have the same associated cost function. And then we find the original production function. That's the result. Okay? So let us make the proof. The proof is not so complicated. Is the statement clear? Is the statement clear? No?
It's the same one.
The same?
The cost function will be same exactly that we got the maximum.
Yes. I mean, forget this equality. Just look at the right-hand side. So yesterday we saw, if we have a cost function and we apply this formula, then we obtain a production function which has the same effect as the original production function, in the sense that the associated cost function is the same. This is true always. But now we are saying more, that if the original production function is quasi-concave, non-decreasing, and upper semi-continuous, this formula that we applied yesterday will give you exactly the same, the original production function. And this is what happened yesterday with the Cobb-Douglas example. Is now the statement clear? Okay. Then the proof is not difficult. Let's give a name to the function defined on the right-hand side. Let's call it g. So we have to prove that f of x is equal to g of x for every x. And we know that f of x is less than or equal to g of x. We saw it yesterday because when I gave this formula, I was trying to recover f, and I say I cannot recover f. But the most I can say is that f is at most this what today we are calling g of x. I mean, the argument is so simple that I will reproduce it now. Okay, the reason was that if you look at the definition of the cost function, then this inequality holds in particular for that given x when y is equal to f of x, obviously. So this means that when we replace here y with f of x, this is the minimum of this, let's say now we should write f of x prime if you want, but then x prime equal s satisfies this condition. So the cost would be less than or equal to the cost corresponding to a feasible x prime, and a feasible x prime is x. Okay? So we have this inequality, and then this means that we have this inequality for f of x for every p, then f of x is one of these i's. Then f of x is smaller than or equal to the largest of these i's. And the largest of these i's is what we call g of x. Okay, so this was the proof I already gave with not using this notation, but to prove this inequality. Is this clear? Okay. So now, thank you. But now we have to prove that equality holds. And let us do it by contradiction. Suppose not. Suppose for some x, we have a strict inequality. We will see that this is impossible. Then take any real number between these two. Call it alpha. So we have f of x less than alpha. This simply means that x does not belong to the upper level set of f corresponding to the level alpha, okay, because this set is defined by f of x greater than or equal to alpha. And what do we know about this set? It's convex and closed. It's convex because our function is quasi-concave, and is closed because our function is upper semi-continuous. Then we can apply the separation theorem that we saw yesterday in your tutorial. So there exists a vector P in Rn. And there is a number K such that the hyperplane, let's say Pz less than or equal to K, contains this upper level set but does not contain X. So such that so this is true for every Z in U of F alpha, but it's not true for X. It separates X from the upper level set. Clear? Now it would be very easy for me to tell you a lie, but I will not. The lie would be that we take P as a price vector, but a price vector is not any vector. Should be strictly positive. Okay, so what we are going to see now. Well, P is not necessarily strictly positive, but is necessarily non-negative. Because, well, first of all, in the exceptional case, when this upper level set is empty, this first part doesn't impose any condition because there is no set. Then you can take any P. And then take any P, strictly positive, whatever you want, compute Px. For instance, P equals 0. And then a larger K equal 1. And that's it. So the empty case is trivial, so suppose it is non-empty. So there is some element, Z bar, I can take an element here, okay? And then I consider this element where EI is the unit vector with 1 in the ith component and lambda is strictly positive. Then replacing, well, this belongs to U of F alpha for every positive lambda. Do you know why? Because F is non-decreasing. Then Z bar was here, means F of Z bar is greater than or equal to alpha. Then this is greater than or equal to Z bar, actually, yeah. And then, so its value is larger than the value at Z bar. So it's greater than alpha. So it still belongs to the upper level sets. And this means that it must satisfy this inequality. But then, if we multiply EI with Z, we get the ith components of P. Okay? And now, if Pi were negative, then since lambda can be made arbitrarily large, it would go to minus infinity as lambda goes to plus infinity, which is impossible because there is a lower bound k. So this shows that Pi is non-negative, and this is true for every component of P. So the separating hyperplane is in R plus n. This is a consequence of the non-decreasingness of our function, as you have seen. So I'm using every assumption. I use that it is quasi-concave and upper semi-continuous to say that the upper level set is convex enclosed, and now to prove that P is non-negative, I use the non-decreasingness. But this is not enough to say that P is a price vector. I need P to be strictly positive. And how can I achieve that? Very easily. If my original P is not strictly positive in all of its components, then I add something strictly positive, and because Z is always non-negative, this will be larger, so it will be still be, even more larger than K. From this side, there is no problem. And from the other side, by continuity, if I increase P a little bit, it will be still smaller than K because the inequality here is strict. Is this argument clear? No? So, I consider P plus epsilon the all one vectors, E, the sum of the SI's. So E is 1, 1, 1. Then, if P does this job, this does this job too, as long as epsilon is small enough. Because for the left-hand side, we have P plus epsilon E Z equals Pz plus epsilon Ez. This is greater than or equal to K, and this is greater than or equal to 0, because everything here is positive. This for what concerns this inequality. But for the other, P plus epsilon E Z equals X. This is Px plus epsilon Ex. And if I want it smaller than K, because Px is smaller than K, I can achieve this just by taking epsilon small enough, namely epsilon smaller than K minus Px divided by Ex, which is positive. How do you know that it is positive? Because, well, E is strictly positive, is 1, 1, 1, 1. Then if X is different from 0, because it's non-negative, then this is strictly positive. But what if X is equal to 0? If what happens in this case. If x is equal to 0, everything should be simpler. We are trying to prove equality here. If x is equal to 0, here we get 0. And C, yes, the cost function less than or equal to 0 means that y is 0. So g of x is 0. And then, f of x. Then g of x is equal to 0, which is what happens with f. F of x is 0. So in that case, the equality is automatically satisfied. Okay? Good. So now I can consider that P.
Sir, where we are using in the argument that we are giving, like P is strictly positive. So where we are using that P is not strictly positive, the argument that we are giving.
No. This argument is to show that if my separating hyperplane is defined by some P which is not strictly positive, I replace it with another one which also separates but is strictly positive. So without loss of generality, I can take P strictly positive. So, what can we say of C of yp in this situation? That C of yp is the minimum of P set such that f of z is greater than or equal to y. That is to say that z is in the upper level set of f corresponding to the level I. And we know that for every such set, we have this inequality. So all these inner products are greater than or equal to k. So this must be greater than or equal to k. So we have C of yp greater than, because k is greater than px. Okay, let's. This is the conclusion. And then this means that for this x, not all these conditions are satisfied. It is not satisfied by that particular P. Okay, so this y is not in this set. And we know that this set we discussed yesterday is a closed interval, 0 f of x. So this means that this y is larger, strictly larger than the endpoint of the interval, which is f of x. And this is the end of the proof. Because sorry, something is missing here. Well, no, wait a second. There is a confusion with the notation because I am considering the alpha level set, and here I am saying the Y level set. It should be the same everywhere. So I can put here Y and there Y2 or alpha in both places. I choose to write Y here. Okay? Now it is correct. Then, so this Y is not among those ones, so is greater than the maximum of those Y's, f of x. But the maximum, the maximum of these Y's is not f of x, it's what we call g of x. So my argument is that this Y does not belong to this set. So is strictly larger than the maximum of the Y's in this interval. And the maximum, we didn't call it f of x, we called it g of x. So the conclusion is that Y is greater than g of x, which is a contradiction. Okay? An alternative way of presenting the same proof. Instead of assuming that the inequality is strict, don't assume anything, then let Y be such that it's equivalent, it's the same, such that this, and then I get that g of x is smaller than any number greater than f of x. So g of x, instead of proceeding by contradiction, then I conclude that g of x is less than or equal to f of x. We have used this argument 1,000,000 times. I said one of the ways of proving is in this expression, since y is arbitrary, an arbitrary number greater than f of x, let's y tend to f of x. So going to the limit, here we get f of x greater than or equal to g of x. Present the proof the way you like now or as I did initially by contradiction. Anyway, we have this and that, so we conclude that equality holds. Is this clear?
Sir, the last argument was not clear to me. Why is greater than gx?
No. This one, okay. So this y, this particular y, is not among these ones, because this condition should be satisfied for every p. And there is one particular p for which it is not satisfied. And remember that This set has the form 0 f of x. It's an interval. So we are saying y does not belong to the interval 0 f of x. And y is not negative. So y, oh sorry. This is g of x. I mean, the maximum is called g of x. Okay? So since y is not here, y is strictly larger than the largest y there, which is called g of x.
There can be y's which are like, okay, this is a whole interval, okay, all the y's will be in that.
Yeah. I mean, we saw it.
Yes.
I mean, we saw that this set is an interval. In principle, might be unbounded, but we proved that it is bounded and it is closed. And it contains 0. Then it's of this type, 0, the maximum. And the maximum we are calling g of x. So y is larger than g of x. Now is it clear? Okay. Thank you. So this explains why yesterday in the Cobb-Douglas example we recovered the original production function. But this also tells us something else. In principle, there are infinitely many production functions that have the same associated cost function. But only one among all of them, only one has all these nice properties. It's quasi-concave, non-decreasing, and upper semi-continuous. Why only one? Because, I mean, you have one production function, you have another production function. Then I compute your cost function, I compute your cost function, it is the same. Then, by this procedure, I compute your original production functions. Since your production functions were regular in this sense, I obtain the same. Because I can recover both of them. But this formula produces only one function. So your function and his function are exactly the same. And also because we observed that this inequality is always satisfied, even without those regularity conditions, then what we know is that this regular, I insist by regular, now I mean quasi-concave, non-decreasing, and upper semi-continuous. This regular production function is the largest among those production functions that yield the same cost function. Okay? So I don't know if you realize that we have proved that there is a bijection between two interesting sets of functions. One, let's say, the class of, let's call it P, calligraphic P, production functions, regular production functions. By this I mean functions, sorry, this is N, functions from R plus N into R plus that are quasi-concave, non-decreasing, and upper semi-continuous. And the set I'm going to call calligraphic C. I mean, this, I insist, are functions from R plus N into R plus and are regular. And these are functions from R plus plus N into R plus union plus infinity, which satisfies 1, 2, 3, 4, 5. the properties we obtain for cost functions that we prove to be characteristic of cost functions. From here we move to there just by defining the cost function. But we can go back by this formula. So this is a bijection. Okay. I think it's a beautiful result. And among other things, it proves, it's one of the many proofs we find in economics, that this generalization of concavity, quasi-concavity, is not an artificial generalization. There are, in my opinion, too many artificial generalizations of convexity. Many notions which lack a proper motivation. Why do you introduce this class of functions? Do they appear in practical problems? If yes, fantastic. If not, what's the purpose of introducing that class of function? Just writing a new paper? I don't like this. And we see it very frequently in generalized convexity. Okay? But here, quasi-concavity appears spontaneously. Okay? So it's closely related to the cost function because the bijection is thanks to quasi-concavity. We will see it again soon in consumer theory, that quasi-convexity appears in a totally normal way. Now we are going to see another result which also relates our economic problem with convexity or concavity, which is very nice, easy to prove, and very useful. So, it's a corollary of this theorem. So let F be as there. A regular production function. And let C be as there. Then, for every y and every p, the solution set of the cost minimization problem corresponding to y and p. So the cost minimization problem is minimize px subject to f of x greater than y. Okay, we want to produce y, so we need inputs that produce at least y, and under this constraint we want to minimize the cost. Then the solution set under this assumption is the super differential of the cost function as a function of p at that particular p. This is a more general version of a well-known result to economists called Shephard's lemma. They only consider the differentiable case. Okay, but we can do it more generally because we are in convexity. I mean, so if you want to solve this problem, find the so-called input demand function or input demand correspondence, which are the optimal inputs x under this prices p for this desired level of output y. Okay? Then you want to find the optimal inputs. They make the solution set of this problem. Then if you know the cost function, simply compute its super differential. What is the proof of this result? Maybe I can erase here because we remember. So I want to prove, let's say that the optimal solution set, let us call it like this, of that problem is equal to the super differential okay? Let us first prove this inclusion. So consider any optimal solution to the problem min px subject to f of x subject to f of x less than or equal to y. What does this mean? It means two things. That first, Z is feasible. So it satisfies but feasibility is not enough. We are saying that it is optimal. So the value of the objective function at this optimal solution is the optimal value of this problem. And the optimal value of this problem is what we had called CYP. Okay, so these two conditions express the fact that Z is an optimal solution. Now we are going to check very easily that Z is a super gradient. Just proving the subgradient or supergradient inequality. So consider any q and r plus plus n, and look at C of yq. C of yq by definition is the minimum of px such that f of x is less than or equal to y. And z is among these x, as we are saying here. So this minimum value is less than or equal to one feasible value, which is, sorry, this is q. Okay, q, q. Then this is less than or equal to q inner product z. And then I hope you agree that nothing changes if I add here 0. You will accept this equality, so I am adding 0. This is 0. It's set here. Okay? So equality is true. End of the proof. Because this is C of yp plus q minus p comma z. Because this holds for every q, this is, z is a super gradient. Do you agree? Where did I use here that f is quasi-concave, non-decreasing, and upper semi-continuous? Answer, nowhere. I mean, the only assumption I used implicitly was that it is upper semi-continuous, because we decided, but even without it, it would work. I mean, we decided from the very beginning that our production function will always be upper semi-continuous, because this allows us to write here minimum. But even if we have infimum instead of minimum, all the argument goes through. So this holds for any production function, not necessarily regular. I mean, even if it is not upper semi-continuous. So, and this observation is very important, that this inclusion holds in general. So regularity I need for the opposite inclusion. So now I take any supergradient of the cost function corresponding to a particular y and a particular p, and I want to solve to show that this supergradient is an optimal solution to this problem with that particular p and that particular y. Then, well, at the beginning the proof is what we have seen going backwards. This means that C of yq is less than or equal to C of yp plus q minus p z, which is the supergradient, for every q in R plus plus n. Moving one term to the left-hand side, the term depending on Q. Okay? And now I can use an argument I have already used. Exactly. So, taking here, because this is satisfied for every Q. Then taking Q equals 2P, and then Q equal 1/2 P. Then I prove that the right-hand side is 0. Which means that this inequality reads C of YQ minus Q Z is less than or equal to 0 for every Q. Now let's show optimality. Consider but listen, I want to prove that this set is an optimal solution. But first of all, it should be an input vector. So it should be non-negative. Is it non-negative? Yes, because of this condition. Okay, again, is this clear? If not, I repeat the argument. From this inequality, I get Q Z greater than or equal to C of YQ, which is also non-negative. We know that. Now, if I take Q, let's say equal to EI plus epsilon times E, for epsilon positive, then Q is in R plus plus N, and so it satisfies this inequality. So this means EI plus epsilon E Z is greater than or equal to 0, but this is EI times Z, which is the ith component of Z, plus epsilon E Z. And then let epsilon go to 0, and then you get that Zi is greater than or equal to 0. This is a very classical argument, which in fact, I should not use it so many times. I should have proved some time earlier that a supergradient of a non-decreasing function has always non-negative components. This is the argument we are using again and again. Okay. So, Z is It's an input vector. But is it feasible for this problem? So what can we say about f of z? Now I am using that f is regular, quasi-concave, non-decreasing, and upper semi-continuous. So f satisfies that formula. The formula that allows us to recover the production function from the cost function when the production function is regular. So this is the maximum of, let's say, y prime, because y is already used, of y prime in R plus, such that px, or c of y prime, let's say q, because p is already used, less than or equal to q z for every q in R plus plus n. But among these y primes, there is our y. This is set here. So this is larger or equal to our y. I'm considering the maximum of all these y primes, and y is one of them. This means x is feasible for this problem. It's a genuine input vector and satisfies the constraint. And now what is the value of the objective function at this particular point? Is c of yp. So the value of the objective function is the optimal value of that problem. So this means that Z is an optimal solution. Okay? But we are going to use later that this inclusion holds for any production function, even if it is non-regular. So a corollary of that inclusion is what economists know as Shephard lemma. Let f be, well, in our context, because we decided that we would never use function, but actually this assumption is superfluous. To be consistent with our framework, but there is nothing else. Let C the cost function with F. I and P, output level then if the cost function for this given y differentiable at P which conditions on the quasi-concave on the production that the cost function is differentiable. I'm going to give an answer. For a moment, suppose that you compute the cost function and it happens. Then of this function at P, the unique to the cost solution is unique, and it's the gradient. The argument, write a single line. And no, really we need, now I notice there may be no optimal solution here. So we really need a persimmon. Then, thanks to a persimmon non-empty, the right-hand side is a singleton. So the super differential reduces to the single. So we have equality, which means the optimal solution, and that element is the gradient. That we will never consider upper semi-continuous. And one of the reasons is this problem has an optimal solution. Okay? Then the optimal solution set is non-empty. And we always have this inclusion. For this inclusion, now the set is a singleton because we are assuming a concave function is differentiable at a point is the singleton of the gradient contained in a singleton. Then it coincides. So the optimal solution set is the single. So there is a unique optimal solution, and this optimal solution is the gradient. Just take derivatives and you get the optimal input set, input vector, because now it is unique. We will illustrate this later, after the break, with Cobb-Douglas. Okay, we are always looking at Cobb-Douglas, but there are always also very many other useful production functions. I will introduce later, they were introduced already by Professor Mishra, the Leontief production functions, then we will work with it also. Okay? But now it's time to the break.